Hello, everybody. Let's continue. So then the next part of the video sequence will then be, we need to talk about determinants and how it works with products, the product of the two matrices. The nice thing is it works fantastically well, but it does take a little bit of time to understand. The minute you have that, then we can finally get to the connection between invertible matrices and how the determinant is not zero. Now you have probably starting to get a little bit overwhelmed by the proofs. That's how the course works. If you're just given theorems very quickly, though, you get to a point where you just start going, I believe, but that means then you won't be able to use them. You get to a certain point where your inability to understand why prevents you from doing computations. And unless you're just told, please, I want you to go over there and do this. Like if you're just told general problems, you can't actually solve the problem. But because you might be feeling a little overwhelmed, in this video, I'm gonna let you skip. So then I'm gonna keep going in the video. But here are the two main results. That if you have any elementary matrix and A is any matrix, then if you ever take the determinant of that elementary matrix times A, it's actually the same as the determinant of just the elementary matrix times the determinant of A. The determinant distributes through that kind of matrix multiplication. That's really nice. That's really nice. And then we have, of course, the big granddaddy result, which is if the matrix is invertible, then the determinant is not zero. That's the one we need in order to compute eigenvalues and in order to get our eigenvectors. So then this is your last chance before I move on. Okay, you've been warned. Let's go talk about that theorem. Try to explain why it is the way it is. So let's suppose you have an elementary matrix, and I'm going to multiply it on the left to a matrix A. So the determinant of that product is the same as the product of the determinants of the separate matrices. Now, why? It's actually just an application of what we just did. So then you just look at each row operation. Because of the three row operations, there's a corresponding elementary matrix. I'll just do it once. I'll just do it for swapping rows. And all the others are done really the same way. So suppose then that E is the elementary matrix that's formed by swapping rows I and J in the identity matrix. Well, but then by the swapping rows theorem I gave you for determinants, the determinant of the new matrix is the opposite of the determinant of the original matrix. But the original matrix is the identity matrix, and that's in diagonal matrix. So then the determinant of that is 1, because that's the product of the entries along the main diagonal. So therefore, the determinant of this elementary matrix is actually -1. But if you take E times A, that matrix is where you take row A and swap rows I and J. So then you can compare the matrix EA, its determinant, with the determinant of just A, because they're opposites to each other, because all you did was to go from one to the other is swap two rows. So the determinant of E times A is negative times the determinant of A. But that negative, think of that as -1, and you get the result that we're after, that the determinant of E times A is the determinant of E times the determinant of A. This is just true for all the elementary matrices. I only showed you reason why in one of the three row operations. Let's now get to then the big bad result. So the big bad result is if a matrix is invertible, that only happens if the determinant of A is non-zero. This is what we need to compute our eigenvalues in general. So it deserves a proof. So let A be any matrix, and R is its reduced row echelon form. Now for that sequence of row operations, there's a corresponding sequence of elementary matrices. So if you just multiply the matrix A on the left by the corresponding elementary matrices, you get R. That's what I just said right there. But then take the determinant of both sides. I just said, though, that if you ever have an elementary matrix times a matrix, you can separate that product. Well, you can do that over and over and over again every time I just, on the left, encounter another elementary matrix. So the left-hand determinant there is this product of the determinants of matrices. But then another sneaky trick is that the elementary matrices are formed by doing a row operation on the identity matrix. So all the row operations, the only thing they do is either take the opposite of the determinant of the old matrix, or take a scalar multiple of it, or don't change it at all. But the determinant of the identity matrix is just 1. So the determinant of each and every one of these elementary matrices is a non-zero number. I don't care what it is, it's a non-zero number. Therefore, that implies that the determinant of A is non-zero if and only if the determinant of its row-reduced echelon form is also non-zero. Okay, we need that for the next part. So remember, the determinant of A is non-zero if and only if the determinant of its row-reduced echelon form is 0. Now we'll start with the proof. Now we have this background. So let's go one direction. Let's assume that the determinant is not 0. I will prove to you that A is invertible. All right, well, we know that if the determinant of A is non-zero, then we know that the determinant of its row-reduced echelon form is non-zero. Well, the only way the row-reduced echelon form would have a non-zero determinant if it has no rows of zeros. Remember, if there's a row of zeros, the determinant is 0. So we now know the row-reduced echelon form has no row of zeros. But the matrix is an n by n matrix. If it has no row of zeros, it has to have a leading entry in every single row and every single column, which means it has to be the identity matrix. So we now know the row-reduced echelon form of this matrix is the identity matrix. Therefore, by the fundamental theorem of invertible matrices, A is invertible. So we now have half the proof. If the determinant is not 0, then A is invertible. Now we do the other way. What if A is invertible? If A is invertible, then by the fundamental theorem of invertible matrices, then the row-reduced echelon form of R is the identity matrix because A reduces the identity. But that would mean then that the determinant of A is not 0. But then we know then that the determinant of, well, we know that the determinant of R is 1 and is therefore not 0. And therefore, since the determinant of R is not 0, then the determinant of A is not 0. So if the matrix is invertible, the determinant is not 0. And that's the result. Neat, right? Okay, so then in the next section, we'll talk about consequences of these things. That's enough for this video.